All right. Good morning, everybody. So I'm going to, I know if you joined I think most people are on Zoom, but if you joined a little bit late, I did post something in the chat. I'm going to repost it, just posted it now, because I know if you joined it a little bit late, you don't see previous messages on the chat, if I'm not mistaken. Can everybody hear me? If you can't hear me, please let me know, although you wouldn't be able to hear me ask you. So somebody give me a thumbs up, like, yeah, I can hear you. Okay, awesome. Perfect. That's good. That's good. So you can also watch the lecture via YouTube if you'd like. You don't have to, but I'm streaming it there as well, just because it's easier to make that playlist, populate that playlist on YouTube. So hopefully that will make things nice and easy. Okay. So I am actually a little bit had it all set up, ready to go. All right, so little bit about me. That's what we're going to talk about now. Gosh, I'm so awkward. I'm sorry, I'm so awkward in the morning. So what you can call me Professor Vrickus, Dr. Vrickus, Dr. Regina, Professor Regina. That's fine too. A good idea to kind of get used to calling people by their professional titles in a professional setting. Took a lot of effort and time, and time spent away from family, time spent not saving for retirement, all that jazz, to get it. So it's a nice thing to do. What I don't really like being called is Miss Frickus, Miss Frickus, just because it makes me sound like a kindergarten teacher, and that's not uh, an insult to kindergarten teachers. They work their butts off, but I just want to make sure that you understand that's not the dynamic that we've got. Like, you're an adult, I'm an adult ish, and so that's the professional relationship that we should have. A little bit about me. I like derpy animals. This is my dog Leela. She's named after Leela from Futurama. I imagine that she speaks in Doug's voice from Up, and we often narrate what she's thinking in at home. I won't do that for you because that's embarrassing. But I also have two cats. I have Knox, as in Harry Potter, Lumos Knox, and Joey Softpaws, as in Joey Softpaws, also because I'm married into an Italian and Greek family, and so I guess we're paying. My husband has a thing with naming them mafia names, so Joey Softpaws. There we go. Um, this is my family. I've got my husband, Chris. I've got Joshua, who's in middle school, and Lily, who's in second grade. Um, so I guess it's everybody's here. You must have found the Canvas page, so that's awesome. I didn't send out an announcement before the semester started telling you where to find things, because I kind of figured that we've all been in this, and just you could probably go to the Canvas page and it's all highlighted. So good on you for finding it. Looks like I've got 32 out of like 40, and yeah, so I think that's pretty good. So you'll see at the top of that Canvas page where it's highlighted, anytime I have like a correction from class or anything like that, that's where I'm going to put it, instead of just sending out an announcement or an email, because like you, I'm inundated with emails, and so after a while I get desensitized from them, and so I'm just gonna, anything I need to tell you, that's where I'm gonna put it, unless it's something super important. Um, all right, so let's see, where am I? There we go. All right, so if you click on syllabus there, you'll come to the syllabus. So nothing really all that exciting. Tells where my office is when we're back on campus. Of course, we're going to be doing this song and dance for the next 2 weeks. But once we're back on campus, my office is in Duke 354, and I'll be in there. I'll go there right after this class, and then I'll be there until my next class around 12 o'clock. So just knock on the door. If it's closed, knock on the door. If I'm not in there, I usually put a sticky note on the door. There's also virtual office hours here. For the next 2 weeks, and there should be a link on Canvas. So if you on the left hand side, that little menu where Zoom is, there should be office hours scheduled in there, and so you should be able to get to me there. Um, So testing, we're going to talk about that in just a bit, but it will be done in person. And so we'll talk about that shortly. And so exciting, you'll be able to celebrate the time that you come back to class by taking a test. So I'm sorry about that. It just kind of worked out that way. I really didn't plan it like that. There will be videos to watch before class, and I do that just because I want to be able to progress through all the material pretty quickly and just be able to use this 50 minutes wisely. Um, so once again, at the top of the home page, you'll see um, links for any corrections or the grader email or anything like that. I just found out who the graders are, so I'll post their email and their contact information there sometime today. There's also a link for equation sheet and tables and problem statements. So the problem statements, those are the things that we're going to go over in class. They're kind of in the form of guided notes. So go ahead and I would, have those handy, print them out or have them on a tablet or whatever you want to do. The equation sheet and tables is pretty large PDF. You don't have to print it all out, just have access to it. I'll provide that to you on testing days, so you really don't have to print it out unless you want to. And if you want the most used pages, I think it's on that updates and announcements. If you kind of scroll down, there's maybe 10 pages or so that we use a lot in this class. If you go to assignments, click on assignments, it'll bring you to the assignments. I don't know, by default, it lists them by date. I would organize it by type, so at the very top you could do that. So you'll see we have 6 tests and then a final exam. The tests are worth 80%, the final exam is worth 20. And you'll see up at the top, I know it's a little bit fuzzy. Oh, by the way, if you're wondering, like, it's super annoying, on Zoom, if you click pin, you'd just be able to look at my image if you haven't figured that already. Figured that out already. So the tests, you'll see that we have 6 of them. They correspond to the 6 units that we've got. So about every 2-3 weeks, you'll have a test. I'll drop the lowest one. I don't give makeup tests because it's usually kind of a nightmare trying to schedule these things, and that's why I do drop the lowest one. So if you happen to get sick, don't come in. It'll just be dropped. No big deal. If you never get sick, then it just means the lowest test is dropped. Okay. If you have accommodations with the Office of Disability, I'll ask you to go ahead and schedule your tests in the disability office, and then I'll have the test and the tables sent to you. I'm not giving homework just because I don't really have the TA support. But I am giving at the very bottom, there are practice tests for each of the units. And then once you hit submit, the solutions will appear to you. So it'll be a good way for you to kind of practice the types of problems that you'll see. And you'll get the same benefit as the homework without the problem of how do I get enough graders to be able to grade tests and homework in a timely fashion. Like I said, the tests are going to be done in person. The only thing you need to bring is something to write with and a calculator, just a cheapo calculator. So on the syllabus, there will be a link to the calculators that are allowed on the FE exam. You could just look up FE exam and calculators and it should pop up as well. Just a cheapo non-graphing calculator, that's non-programmable calculator. That's what I'm looking for. The way that it will go, you'll come in, you'll be provided with everything. Take your test, you'll have scratch paper and everything. Take your test, and once you're done, you'll come up and you'll turn in the hard copy. But at my desk, you'll scan in your work and you'll also upload it to Canvas. The reason that I'm going to do it like that is because that way I don't have to, I'll be able to get all that stuff to my grader more quickly. And so hopefully that will result in quicker grading, number one. And number two, you don't have to keep up with the paper. And, if Yeah, I like the paperless stuff anyway. You won't have to keep up with the paper. If you have questions about your exam and you ask me after I've gone home and your test is sitting in my office, it doesn't really matter. I can go pull up your test. I think it'll just be a lot cleaner. But you do need to turn in both things. You need to hand me the hard copy and then also upload it. If I don't have the hard copy, then I can't grade your test. Okay, so got to have the hard copy. That's to prevent you from kind of going and sitting down, sending, scanning the test to somebody in India saying, hey, solve this work. Here's my login information. Log it in for me. Awesome. Thanks. Right. So I need the hard copy before you walk out of the test. Okay, there is also this, like, under ungraded assignments, there's an exam example, exam upload and submission example. So that'll help you make sure that you can scan in a PDF with your phone and then upload it to Canvas. So you're going to have to download the Canvas app and also a scanner app. I really like Adobe Scan. Works pretty well, and I'm pretty sure there's no spyware or anything in it, unlike forget the one that got in trouble, Cam Scanner, a couple of years ago. Yeah, so let's see what else we got. Like I mentioned, I'm also streaming this on YouTube, so videos will be there, but there are also the videos that you need to watch prior to class. I know it says Thermo 2 there. There's one for Thermo 1 as well. And the lecture for today is going to be populated in that Thermo 1 playlist. As far as what videos to watch and when, if you click on class schedule, there'll be a Google Doc that just has my kind of rough schedule. So as far as what we're covering what day, that may fluctuate a little just depending on how fast we're progressing, but the exam dates I don't intend to change. So, unless there's some act of God, that we have to change it, we're going to keep those as they are, so you can hopefully plan throughout the semester about how everything's going to go. All right, so if you don't have any questions, I'm going to start plugging along here. So this is the PDF of the problem statement. So if you go to the Canvas page and you click on problem statements, it's the one for Unit 1. That's where I've got this. Okay. And if you do have questions, please just say, you could talk. You could talk. Or you can throw something in the chat. I'm more likely to hear you. It might take me a second to look up and notice that somebody's written something, but you are more than welcome to interrupt me in the class, okay? Okay. Everybody good? Oops. I have too many monitors, and there we go. That's bothering. Okay. So if you watched video 1.1, great. If you didn't, it's okay. We're going to go over it pretty quickly right now, but I would suggest that you do watch that video if you haven't. So a thermodynamic system, it's a region of space or a chunk of mass. Just like that word. It's a chunk of mass that you have chosen to analyze. A closed system, or sometimes you'll hear it referred to as a control mass. That's the chunk of mass. An open system, I think more you'll hear outside of this class, you'll hear it referred to as a control volume. It's the same thing. I'm used to saying open system, but if you hear control volume, that's what they're talking about. That's your region of space. And they kind of sound the same, but they're not. So when we have a chunk of mass, oftentimes maybe we're talking about a gas in a piston cylinder. So here's my piston cylinder. And your chunk of mass is everything that's within the inside of that piston cylinder. Or it could be the whole whole apparatus, it doesn't matter, but it's a chunk of mass. So you may be looking at it for a process, but it's the same mass. You start out with 5 kilograms of mass, you end up with 5 kilograms of mass. The control volume is, classic example would be you've got pipe flow. So you've got flow in and you've got flow out of this chunk or this region of the pipe, and you're interested in how, I don't know, how characteristics of that fluid that's flowing through that pipe, you're interested in how things change from the inlet to the outlet. You would model it as an open system or control volume. So it's important to be able to look at a problem and know, do I have a closed system or an open system? Because the equations that we use can be slightly different depending on which type of system that you have. So that's all video 1.1. Video 1.2 talks about properties, states, processes. So a property is just a characteristic of the system. And we've got two different types of properties. We've got extensive properties and intensive properties. So an extensive property is dependent on the size or the mass of a system. So this is dependent on the size or the mass of the system. So an example of that would be volume. And in this class, we'll use a capital V to indicate volume. An intensive property is independent of the size or the mass of the system. I just don't want to write that down again, but independent of the size or the mass of the system. So an example of that would be temperature or pressure. So we use capital P for pressure, capital T for temperature, easy peasy. So a way to think about that is if, in the room that you're sitting in, the temperature, it doesn't matter whether the room was, doubled in size, the temperature and the pressure would be relatively the same. We're not talking about local spots, right? I mean, right around you, maybe the temperature is a little bit higher, but overall, the overall temperature is the same. So it doesn't matter whether you're talking about this little chunk of air or the air in the entire room. So intensive properties, they are used to fix the state. And the state is, these are kind of like really hand-wavy definitions, but it's defined by the characteristics. What that means is when we say fix the state, we'll see in just a bit, if you know a handful of properties about a system, then you can figure out any other properties that you want to know because they're all kind of related. So you just need to know, typically two, you need to know two, but those properties that those known properties, they have to be intensive properties. So extensive properties, great, but they won't help you fix the state. It's the intensive properties that will. A specific property is when you take an extensive property and you make it an intensive property, and you do that by dividing through by the mass. So this is an extensive property divided by the mass. So divided by the mass expressed on a per mass basis. And this will give you an intensive property. And an example of this would be specific volume. So specific volume is your volume divided by your mass. So it's on a per mass basis. The units maybe, if you're an SI units, it'd be meters cubed per kilogram, or feet cubed per pound mass if you're in English units. All right. Process. This is how you get from. Oops, I'm sorry. This is how you get from one state to the other. So. So this is from, let's say, state 1 to state 2. And this is going to be something that's a PV diagram. So for example, and it doesn't really matter for the purposes of what I'm drawing now, but I'm going to graph how temperature and specific volume are related to one another. So say from state 1, maybe it's at this particular temperature and pressure. This is state 2, it's at this temperature and temperature and specific volume. And then the process path that connects them might go something like that. It doesn't have to be a straight line. Sometimes it's not. Often it is not. Yeah. All right. So we talked about properties. So video 1.3 goes into a little bit more detail on the 3 intensive properties that we're going to start out on. So this is actually a lowercase v here, so it's specific volume, temperature, pressure, and specific volume. Talked about specific volume already. Specific volume would be volume divided by the mass. If you're more familiar with density, it's just the inverse of density. So that's not a P, that's rho. So 1 over density. Temperature, we've got 4 units for temperature. So we've got degrees Celsius, degrees Fahrenheit, but we also have absolute temperature. So absolute temperature know why it's going to bother me that it's not in the same color. Absolute temperature. So absolute temperature units. In SI units, this is Kelvin. So the way that you're going to get from degrees Celsius to Kelvin is you're just going to add 273 to it. So it's 273.15, but in class I'm just going to use 273, and that will give you temperature, the temperature in units Kelvin. So it's just FYI, it's not degrees Kelvin, it's just Kelvin. In English units, it's going to be Rankine. So to get from degrees Fahrenheit to degrees Rankine, so that you would add 459.67, I think, but I'm adding just 460 in class, and that will give you temperature in, and this is degrees Rankine. As far as, do you need to convert all degrees Celsius to degrees Rankine or all degrees Fahrenheit to degrees, do you need to convert everything to absolute temperature units? Sometimes yes, sometimes no. When in doubt, go ahead and convert. So if you find yourself multiplying by a temperature, put it in absolute temperature units. So either Kelvin or degrees Rankine. So we'll talk about that more. I'll just say when you're doing calculations with temperature, when in doubt, put it in absolute. You can't go wrong. Pressure, got lots of units for pressure, right? We've got bar, ATM, PSI, kPa, kilopascals. The important thing to remember is that properties are evaluated at the system pressure. So properties are evaluated at the system pressure. Okay. System pressure or absolute pressure. Absolute P, absolute pressure. So that's different from gauge pressure. So the system pressure or the absolute pressure, so it's a little bit smaller. So I'll put this as SYS or P absolute. You'll see it referred to both ways. I'm just going to leave it as P without a subscript. That's the system pressure. But this is equal to your gauge pressure plus your atmospheric pressure. So atmospheric pressure being 14.7 psi, 1 atm, something like that. Okay. All right. So if you looked at the, if you did look at the syllabus, there's a little some verbiage in there towards the bottom about including given, find, assume, and solution. So typically, I like to see all four of those things. I say typically because in this first problem, I'm not going to put it just because this is kind of a one-word answer. But typically, that is what you want to do. And so we'll get in a habit of making sure that we list all of those things. So first problem, determine whether it would make more sense for us to use an open or closed system model for the following. It's a short answer. You don't need to write given, find, assume, or solution. So the first one is you want to know the temperature of a gas within a sealed piston cylinder. You want to know how it changes as you compress it. So how should you model the gas? So if you know, let's put something in there. You can put O or C for open or closed. So let's see. Yeah. So your system is everything that's in here. Yeah, there we go. So yeah, I've got some answers for closed in the chat. So that's perfect. And if you didn't get it right, that's okay, right? I this is where you should make mistakes. So it is a closed system because it's the chunk of mass. Your mass isn't changing from state 1 to state 2, from the initial state to the final state, right? It's the same chunk of mass. You started out with, say, 1 kilogram, you end up with 1 kilogram. It's the same 1 kilogram. All right, so now part B, oh, and I should probably write that, it's closed. Part B, you've got flow. You've got a pipe, I don't know, and you're looking at a particular section. And this one should be pretty easy because we drew something, yeah, perfect. We drew something very similar to this when we talked about what an open and closed system is. So I already got a couple of opens. Yes, it's open. So the distinguishing feature about an open system is that mass crosses the boundary. And that boundary is that red dotted line that I've drawn around my system. So it's an imaginary red dotted line, but that's my boundary. Everything that's within the confines of that boundary, it's the system. Everything that's outside of it is the surroundings. So mass is crossing that imaginary red dotted line, so I know it's an open system. All right, so part C, we have a sealed rigid tank. It contains a substance which undergoes a chemical reaction, and you want to know how the overall pressure changes during the reaction. So here's my rigid tank. This is state 1, and this is the same tank at state 2. And so, I start out, it's a chemical reaction. Maybe I start out with components A and B, and then there's some chemical reaction, and I get component A and B, and then I get component C, right? So yes, perfect. So I got the answer that I wanted. It is closed. Why is it closed? It's because the mass doesn't cross the boundary, right? It may be in a different form, but it's the same mass. The mass did not cross that dotted line. All right, so now we got the same rigid tank, but this time we open a valve, right? Perfect. See, you got it now. So somebody already beat me to the punch. It is an open system. So, you know, now you've got mass going out. So you'll note that mass is not coming in and out. It doesn't have to come into and out of like we did with the pipe flow example, but it is crossing the boundary, just going out. Okay, so it is an open system. All right, perfect. All right. So once again, if you do have questions, just say something in the chat. It's great. All right. So problem 2, if you haven't done well, who hasn't done unit conversions if you've gotten this far? But I've ceased to be surprised when I see people still struggling with unit conversions. So if you are still struggling with unit conversions, stop doing that. Get it right now. Figure it out now. You make your life a lot easier, right? Especially when we deal with English units, because I have a mix of SI and English units. So you want to get comfortable with both. So I went ahead and put it in all the given, find, assume solution format just because it's super annoying otherwise. So, and I also have the final answers for all of these because I'm not going to take the entire class period to go through problems A through H, but I will go through the first 1 or 2 just to, you know, if you need a little refresher on unit conversions, we can go ahead and do that. So first one, we want to convert 1.3 liters to inches cubed. So let's do that. Okay. So here is my solution. Put him over here. Oopsies. There we go. All right. So for A, we have 1.3 liters, and I need a conversion factor. Need a conversion factor. So if you look on the home page of the Canvas site, you'll see a link for equation sheet and tables, and that's this guy right here. So I'll give you just a second to look to find that if you don't have it already ready to go. First 2 pages are just, you know, the table of contents, because you see there's a lot, right? Almost 100 pages to go through. But fortunately for you, just need this one right here. So we're going to go to page 5, conversion factors. Okay. So I've got things in liters. Of course, I need to looking at volume. So, and I need it in inches. Is that what I need? So, yeah, inches cubed. So I don't have something that goes directly to inches cubed, but I do have this one. So that goes to feet cubed. Oh, you're good. You got it in your head. See, I'm not that good about the conversion factor. straight from inches cubed to feet cubed, but that's good. Maybe you just typed it in your calculator. You got it. So that's fantastic. But I don't have that, so I'm going to show you just how to get from using those unit conversions, because that's what you'll have on your equation sheet, or that's what you'll have during the test. You'll have that equation sheet during the test. So the conversion factor between liters and feet cubed, it was 0.0353 feet cubed. Okay, perfect. And then, I mean, right, I think we all know, and it's on your equation sheet as well, that there's 12 inches in a foot, but we're not interested in feet, we're interested in feet cubed. So this is feet cubed as well. So if I just go through and make sure my units work out, so I got a feet cubed, I got a feet cubed. Of course, that Yeah, and then this liter, hopefully what I should get is 79.3 inches cubed.
Excuse me,
Yeah,
Professor?
yes.
Do you want us to take into account significant figures when doing dimensional analysis?
So I'm probably not as, I usually don't count off for it. Yes, it's a good practice. It's a good practice to do is to take into account significant figures, because you don't want to report like 10 significant figures to pretend like you're more accurate than you actually are. So I'll say short answer. Uh, yes, go ahead and take into significant figures, but don't stress about it too much for this particular class. Sound good? There'll be
Thank
other
you.
things to stress about as well. All right. So I'll do one more and then we'll kind of call it good. But once again, the final answers for this particular problem, just in case you need a little bit of review, are up there. So part B, we've got joules to BTU. So this is an example of where we need to go from SI units to English units. So I'm going to go back to that conversion factor sheet again. So page 5 of the equation sheet and tables packet. So this is BTU in joule. This is a unit of energy. So looks like right there we got a kilojoule, we got a joule. Perfect. Looks like maybe that one's the one that I want right there. So of course this is kilojoules to BTU. That's fine. We can convert this to joules. So 0.9478. 9478. So 0.9478 BTU. That's 1 kilojoule. And 1 kilojoule is 1,000 joules. Go. Can make sure our units work out. Ba-dump, 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 and all we're left with is the BTU. And so, what is that going to get me? 0.8009. 0.8009 BTU. So just get in a habit. I'm particular about units, so if you get a unit conversion wrong, typically on a test, it's usually like 3 points for each unit conversion issue. So which is not, honestly, not that bad. Some instructors will penalize you a lot more because unit conversions, well, you mess something up, you can kill somebody. So, okay. So I'm going to go ahead and kind of skip over the rest of the unit conversions, but you are welcome to, if you wanted to go over those during office hours, just pop in and I'm happy to walk through those. All right, problem 3. Let's see. So we've got 12 minutes left. Just making sure we're doing good on time. So we read the pressure in our tire is 33 psi. We want to know at what pressure you should evaluate the thermodynamic properties of the air in your tire. And the answer is really, you want the system pressure, right? So what's given to us, we've got our gauge pressure, which is 33 psi, and that's pretty much all that's given. But we want to find the system pressure. So we have a formula. It's the gauge pressure plus our atmospheric pressure. And so one thing, here's, yes, perfect. Thank you, Gunnar. Awesome name, by the way. So here's an example of an assumption that we could make, because they don't actually tell us what the atmospheric pressure is, right? Let's just say it's 14.7. So 14.7 SI. Yep, so you're right. 33 plus 14.7, and they're both in PSI. Yeah, so 47.7 psi. Perfect. Okay, moving right along. Yes. All right, so problem 4, we got a 2-pound mass of an unknown liquid occupies a volume of 72.6 inches cubed. And we want to find the specific volume and the density. So go ahead and write that. I want the specific volume. And oftentimes, most of the time, I will remember in the problem statements to specify what units that I want it in. If I don't specify what units that I want it in, then it's up to you. You report whatever the most convenient ones are. So, but I should always remember to tell you what units I want. And then of course we want the density as well, and we want that in pound mass per feet cubed. Shocking, they're the reciprocal of one another. So there you go. All right. So given, well, we've got 2 pounds of mass, and I'm going to actually write with a little m there just so I differentiate it from pound mass versus pound force. Occupies a volume, so our volume is 72.6 inches cubed. And I guess that's about it. So, I mean, really, this is so easy. It's just plug and chug, but we're really getting practice, putting it in this given, find, assume, solution format. A lot of times you won't have any assumptions, especially for unit 1. Sometimes you don't have any at all. That definitely won't always be the case, but just go ahead and get used to writing the word assume or assumptions just so you have a placeholder, and then put the assumptions as you go, as you start solving the problem. So yeah, feet cubed per pound mass. Well, I guess need the volume. So our specific volume, it's going to be volume over the mass. So I've got 72.6 inches cubed per 2 pound mass. Really the only thing I need to do is just make sure my units work out the way that they're supposed to. So 12 inches cubed is equal to 1 foot cubed. And so let's see what that gets me. 0.02101. 0.02101. Yeah, I guess probably just leave it as 0.2. And then this would be feet cubed. Yes. Probably should go ahead and box that answer, so I'm all happy with it. And then, B is just your density, which is the inverse of that specific volume. So, yeah, 47.67. There's a decimal there, 0.6 pound mass per feet cubed. We don't work in Thermo, we don't usually work with density. We usually work with specific volume. But I guess it's important to know that they are related. I guess it is important. Problem 5, I mean, see, it's setting you up that, Thermo 1 is easy. So first, part A, and I'm going to ignore the given, find, assume stuff, but we want to convert this stuff to absolute temperature units. So for 81, all we're doing is adding 273. For degrees Fahrenheit, we're adding 460. Just so you know, I'm going to go to my equation sheet and tables. Show you where this stuff is. Ooh, yeah. So you do have an equation sheet. This is on the 3rd page of that packet. I don't think I have the conversion factor for degrees Rankine and Kelvin, but they are at the bottom of that conversion factor sheet. So if you, it doesn't matter. If you add the 0.15, it's fine, but typically I don't. All right. So, I mean, just plug and chug. 354, 354 Kelvin, not degrees Kelvin, and then 537 degrees Rankine. So Kelvin, not degrees Rankine, or Kelvin, not degrees Kelvin, but Rankine is in a. All right, problem 6. We're almost there, 5 minutes, and then we're done. So we want to know what the change in specific volume of a 1 pound mass of system is at it as it undergoes a change in volume, and that should be not from 1 feet. It should be a to the minus 3. It should just be to the third. But we want to find the change delta in specific volume of a 1 pound mass sample, a 1 pound mass. And then we're looking at a process from state 1 to state 2. So state 1, and we're going to use a subscript when we're talking about what state we're in. Keep in mind, or keep getting the habit of writing a subscript when you're talking about state 1 or state 2. That's going to be really important because you can get mixed up about what state am I actually talking about. But state 1 is 1 feet cubed, and V2 is a tenth of that, so 0.1 feet cubed. You'll notice I didn't put a subscript beside the mass, and that's just because this is it's a control mass. It's a closed system. This is the same. We could put it as M1 and M2, but it doesn't really matter because it's the same chunk of mass. All right. When we talk about changes in properties, so delta, specific volume, in this case, it's what it is after minus what it is before. So what it is after is V2, and what it is before, is V1. All right, so now that we've put it in this format, we can see, okay, well, I've got volume and I've got mass. Well, specific volume would just be volume divided by mass. You could put that as M1 and M2. It doesn't really, oh shoot. I just said what it is after minus what it is before. Sorry about that, 2 and 1. And so you could put this as 1 over M times V2 minus V1. But yeah, whatever you do, it ends up being negative 0.9 feet cubed per pound mass. Okay, perfect. All right, and so you got that negative there showing that there is a decrease in the specific volume from state 1 to state 2. All right, so we do have 3 more minutes left, and I'm not going to cover any new things. However, I will tell you, this video right here, make sure that you watch it. So I would say for the next time that we meet, video 1.4 through 1.7, I would spend some time getting comfortable with that, because what we're going to have to learn how to do is figure out what phase something is in. We typically are looking at the liquid and the gas phase, and so you have to figure out, is it in a liquid, is it in a gas phase, or is it a mixture of the two? We call that saturated. And you need to be able to do that because you need to be able to look up properties, and you need to be able to use these tables right here. So go ahead and get used to it now. Go ahead and if you can't read those tables, if you can't figure out what phase your particular substance is, in this case water, if you can't do that, you're going to struggle for the rest of the class. So I would encourage you, make sure that you spend some time watching those videos, and then we'll go over what you saw the next time, okay? All right, that's all I've got. I'm going to pop on over to those office hours, and once again, the link is on Zoom, so you can pop over there as well, okay? All right, thank you guys. I appreciate it. Y'all have a wonderful day, and I will either see you in office hours or I will see you next time, okay?
Thank you.
Thank you.
Thank you.